Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is switches in series DC circuits. Our objective is to examine how opens and shorts influence electrical properties of series DC circuits. This lecture operates under the presumption that viewers watch the series DC circuit properties and the DC voltage divider rule lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, only dimly recall their contents, please take the time to do so now. You'll no doubt recall that series circuits exhibit the following properties. Current through elements in series is the same, and for any closed loop, the summation of voltage rises equals the summation of voltage drops. As a preparatory exercise, consider this series circuit consisting of a 72-volt source, R1 having a value 800 ohms, R2 having a value 400 ohms, and R3 having a value 600 ohms. As an exercise to the viewer, I invite you to solve for the voltage drop across, the current through, and the power dissipated by each individual element in this system. Additionally, solve for source current and total power. Use whatever techniques you wish. My only request is that you get the correct results the first time in the shortest time possible. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. Current through elements in series is the same. For this circuit, I source equals I1, which equals I2, which equals I3. The sum of voltage rises equals the sum of voltage drops. For this circuit, E equals V1 plus V2 plus V3. In summary, what goes up must come down. Finally, power in equals power out. For this circuit, power total equals P1 plus P2 plus P3. An application of the voltage divider rule demonstrates the voltage drop across resistor 1 to be 32 volts. An application of Ohm's law demonstrates current through resistor 1 will be 40 milliamperes. Current through elements in series is the same. I source equals I1, which equals I2, which equals I3, and they all equal 40 milliamperes. An application of Ohm's law demonstrates the voltage drop across resistor 2 to be 16 volts. An algebraic rearrangement of the Kirchhoff's voltage law equation for this circuit demonstrates V3 to be the remaining 24 volts. Power is equal to voltage times current. P1 is equal to V1 times I1. Substituting in given values demonstrates R1 dissipates 1.28 watts of power. P2 equals V2 squared divided by R2. Substituting in our given values demonstrates resistor 2 dissipates 640 milliwatts of power. P3 equals I3 squared times R3. Substituting in our given values demonstrates resistor 3 dissipates 960 milliwatts of power. Power in equals power out. For this circuit, power total equals P1 plus P2 plus P3. Substituting in our calculated values demonstrates that power total is 2.88 watts. As a means of checking our work, total power is equal to supply voltage times source current. Substituting our given values also yields 2.88 watts. I've got a reasonable degree of confidence these answers are correct, and we can move on with the rest of this lecture. Let's use these properties to assign nodal voltages in this system. Let's say we ground reference the negative terminal of the source and assign the following nodes, A, B, and C. See if you can use Kirchhoff's voltage law to determine the following voltages with respect to ground. VA with respect to ground, VB with respect to ground, and VC with respect to ground. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Starting at ground and traveling in the clockwise direction, we first encounter a 72-volt rise. VA with respect to ground is undoubtedly 72 volts higher. Traveling from A to B, we encounter a 32-volt drop. Point B must therefore be a 72-volt rise, less a 32-volt drop, or 40 volts higher than ground. Continuing to travel from B to C, we encounter a 16-volt drop. Point C must therefore be a 72-volt rise, less a 32-volt drop, less another 16-volt drop, or 24 volts higher than ground. Let's use these electrical properties as a basis of comparison for our discussion of opens and shorts in series circuits. Copy these results down, or take a screenshot of these results for later use. Let's discuss opens first. As you are no doubt aware, a series path is an inline arrangement of elements such that one path for current exists. If there is an open or loss of connection anywhere in that series path, no path exists for current and no current will flow. In summary, an open anywhere in a series path will stop all current flow through all elements in that series circuit. If no current flows through any element, no voltage will be dropped across any element. Given every voltage rise is accompanied by an equal and opposite voltage drop, any voltage rise induced by the source will be dropped across the open. I say again, an open halts all current flow through a series circuit. If no current flows through any element, no voltage will be dropped across any element, and any voltage rise induced by the source will be dropped across the open. Allow me to demonstrate. Consider a two-terminal switch installed between the positive terminal of the source and the top of R1. You'll recall the resistance of an ideal closed switch is 0 ohms and will allow current flow through the system, whereas the resistance of an open switch is infinite and will not allow current flow through the system. You'll note the inclusion of the two-terminal switch necessitates an additional node I'm calling A single prime. In the closed state, the ideal switch presents 0 ohms of resistance and 40 milliamperes of current travels through the circuit, as our previous analysis suggests, with one minor modification. The switch is an additional element where we can calculate the current through it and the voltage across it. Current through elements in series is the same. The current through the closed switch is undoubtedly 40 milliamperes. Voltage is current times resistance. 40 milliamperes times 0 ohms yields a 0 volt drop. As anticipated, the voltage drop across the ideal switch is indeed 0 volts, and its presence has not influenced this system. Voltage at A with respect to ground would remain 72 volts, and given a 0 volt drop across the switch, voltage at A prime with respect to ground would also be 72 volts. All other properties remain unaffected. VB remains 40 volts and VC remains 24 volts. If, however, we open the switch, an open or infinite resistance exists between the positive terminal of the source and the top of R1. No circuit exists and no current flows. Source current equals 0, as does I1, I2, and I3. Given no current travels through any element, no voltage drop will be experienced by any element. V1 equals 0 volts, as does V2 and V3. Given no voltage across nor current through, no element dissipates any power. P total, P1, P2, and P3 all equal 0 watts. Given a 72 volt rise, all voltage will be dropped across the open. In this case, the gaping hole between the positive terminal of the source and the top of R1, A to A single prime. A voltmeter placed across the terminals of the switch would register a 72 volt differential. If you want to think of it this way, anything touching the positive terminal of the source is charged up to 72 volts, and anything touching the negative terminal of the source is 0 volts. A huge backup of potential exists across the open switch, just waiting for the switch to close. With regard to the nodal voltages with respect to ground, VA with respect to ground would be 72 volts, and VA single prime, VB, and VC would be 0 volts with respect to ground. You will again note that all voltage appears across the open, A to A single prime. Switches and opens can appear in other places in series circuits with similar effect, yet slightly different properties. Consider the same series circuit with a two-terminal switch installed between the bottom of R1 and the top of R2, B to B single prime. In the closed state, the presence of the ideal 0 ohm resistance switch does not influence this system, and 40 milliamperes of current will continue to flow through this system. You'll note the inclusion of the two-terminal switch necessitates an additional node I'm calling B single prime. In the closed state, the switch presents 0 ohms of resistance and current travels through this circuit, as our previous analysis suggests, with the addition that the ideal switch experiences 40 milliamperes of current through it and experiences a 0 volt drop across it. VA with respect to ground will remain 72 volts, and given a 32 volt drop across R1, VB with respect to ground will remain 40 volts, and given a 0 volt drop across the switch, V single prime with respect to ground would also be 40 volts. VC with respect to ground remains 24 volts. If, however, we open the switch, an open or infinite resistance exists between the bottom of R1 and the top of R2. As previously, no circuit exists and no current flows. Source current equals 0, as does I1, I2, and I3. Given no current traveling through any element, no voltage will be dropped across any element. V1 equals 0 volts, as does V2 and V3. Given no voltage across nor current through, no power would be dissipated by any element in this system. P total, P1, P2, and P3 all equal 0 watts. All voltage will be dropped across the open, in this case the gaping hole between the bottom of R1 and the top of R2, B to B single prime. A voltmeter placed between the terminals of the open switch would register a 72 volt differential. If you want to think of it this way, anything touching the positive terminal of the source is charged up to 72 volts, and anything touching the negative terminal of the source is 0 volts. A huge backup of potential exists across the open, just waiting for the switch to close. In this configuration, you will note that both ends of R1 are at 72 volts. This is different than our previous configuration, and perhaps a little counterintuitive because we know R1 experiences no voltage drop if no current flows through it. I must remind you that voltage is a 2-point measurement, with one end of R1 at 72 volts and the other end of R1 at 72 volts, no voltage differential exists and no current flows. A voltmeter placed across the terminals of R1 would demonstrate a 0-volt drop. All voltage will be dropped across the open switch B to B single prime. With regards to nodal voltages with respect to ground, VA with respect to ground would be 72 volts, as would VB. V single prime with respect to ground would be 0 volts, as would VC with respect to ground. All differential occurs across the open switch, B to B single prime. You'll note that a break or open anywhere in a series circuit halts all current flow through the entire series circuit. Perhaps one of the most important applications of this property is the ability to turn a circuit on or off at the flip of a switch. An open switch anywhere in a series circuit completely powers off all elements in that circuit. Consider a switch between the positive terminal of a source and an electrical load. This is known as high-side switching arrangement, where the state of the switch selectively connects or disconnects the series elements to the source. In summary, switch open, everything off, switch closed, everything on. Alternatively, consider a switch between the bottom of the electrical load and the grounded negative terminal of the source. This is known as a low-side switching arrangement where the electrical load is always hooked to the source. However, the state of the switch selectively connects or disconnects the return path to the grounded terminal of the source. As previously, switch open, everything off. Switch closed, everything on. Although this arrangement is functionally equivalent to a high-side switching arrangement, it's perhaps not the safest means of doing so. I'll explain why in later lectures on circuit protection elements in series circuits. I will, however, leave you this clue. Consider an open low-side switch, whereby some errant conductive element accidentally touches the electrical load. What happens? Tune in to the circuit protection element lecture and see if you're right. One last comment about opens in series circuits before we check out shorts. Consider two open switches in this same series circuit. Where does the voltage drop occur? If you said anything other than across the open, you're wrong. Given a 72 volt rise, all voltage will be dropped across the open. More appropriately, which open? The answer is across the large open from node B to node C single prime. Again, if you want to think of it this way, anything touching the positive terminal of the source would be charged up to 72 volts, where anything touching the grounded negative terminal of the source would be at 0 volts. A 72 volt differential will be observed across the larger open. You note elements floating in the chasm between the two opens, i.e. nodes B single prime, R2, and node C, are effectively isolated from the circuit and have absolutely nothing to do with it, and could not be used to measure any differential in the system because they're not part of the system. All voltage is dropped across the open, being the large gap between the two open switches, nodes B and C single prime, with some actual connection to the source. Moving on, let's now examine shorts inside series circuits. A short is a low or 0 ohm resistance path in parallel or around an element. Consider our original series circuit, only this time we include an ideal 0 ohm switch in parallel with R1. With the switch open, no current can pass through the switch and all current will be restricted to the original series circuit. All our previous observations will remain true. If, however, we close the switch, a 0 ohm path is placed in parallel with R1. Think about it. When presented with an 800 ohm path or a 0 ohm path, through which would a majority of electrons travel? Undoubtedly, the 0 ohm short presents a far easier means of travel from end to end. All current will be routed around the shorted 800 ohm resistor. The resistor shorted by the closed switch effectively presents a 0 ohm resistance path, and it can be removed from consideration. With no current traveling through resistor 1, there will be no voltage drop across it. Ordinarily, the source sees a total resistance of 1.8 kiloohms. If, however, current is routed around the shorted 800 ohm resistor, the total resistance seen by the source is the series combination of the remaining elements. 400 plus 600 equals 1 kiloohm. Total resistance seen by the source is decreased. Given the same supply voltage and reduced total resistance, we should expect current to increase. If current increases, we should expect voltage dropped across the remaining elements to increase. Let's see if this is the case. Source current is supply voltage over total resistance. Substituting in our given values yields 72 milliamperes of current. Source current did indeed go up. Current through elements in series is the same. I source equals I2, which equals I3, and they all equal 72 milliamperes. You'll note no current travels through R1, but rather 72 milliamperes of current is routed around it via the closed switch. Given no current through R1, R1 will experience no voltage drop. The voltage drop across R2 will be equal to the current through it times its resistance. V2 equals I2 times R2. Substituting in our given values demonstrates V2 to be roughly 28.8 volts. Given increased current, the voltage drop across R2 understandably increased. Similarly, the voltage drop across R3 will be equal to the current through it times its resistance. V3 equals I3 times R3. Substituting in our given values demonstrates V3 to be the remaining 43.2 volts. Again, given current increase, the voltage drop across R3 understandably increased. In summary, shorted elements in series circuits effectively remove the shorted element from consideration. Given a reduced total resistance, source current will understandably increase. Given increased source current, the voltage drop across the remaining elements will also understandably increase. Think about the implications of both increased current and increased voltage for the remaining elements. The remaining elements must undoubtedly experience more power. Power is voltage times current. Substituting our given values for R2 demonstrates it dissipates an increased amount of 2.1 watts of power. Similarly, R3 dissipates an increased amount of 3.1 watts of power. R1, the shorted element, experiencing no voltage nor current, dissipates no power, effectively kicking back and letting these two suckers carry the increased load. It is for this reason shorts are sometimes dangerous in series circuits because the shorting of a critical current controlling element causes the current through all remaining elements to substantially increase and thus experience more voltage and dissipate more power. In our original circuit, all elements dissipated less than 1.5 watts each. However, in the circuit including the shorted R1, the remaining elements dissipate substantially more power and run the risk of damage if lower power components are specified. Alright, I'm hoping this discussion of opens and shorts in series circuits was pretty easy given your previous understanding of series circuit analysis. As such, let's bring this lecture to a close with one more illustrated example problem. Consider the series circuit consisting of a 16-volt source, R1 having a value of 180 ohms, R2 having a value of 360 ohms, R3 having a value of 270 ohms, and two switches, switch 1 and switch 2. As an exercise of the viewer, I invite you to solve for the voltage drop across, the current through, and the power dissipated by each individual element in the system for 3 different scenarios. Scenario 1, both switches are open. Scenario 2, switch 1 is closed, switch 2 is open. In scenario 3, both switches are closed. By all means, pause the lecture and try this on your own. If you're looking for a hint, here it is. If switch 1 is closed and switch 2 is open, this would create a series combination of all 3 elements. However, if both switches are closed, this would create a series combination of only R1 and R3. R2 would be bypassed by the switch and effectively removed from consideration. If you're tracking, you should have obtained the following results. Scenario 1 should be easy enough. With both switches open, there is no path for current. No element experiences a voltage drop, nor does any element dissipate any power. The closure of switch places R1, R2, and R3 in series with one another for a total resistance of 810 ohms. As a result, the 16-volt source pushes 19.8 milliamperes of current through this system and supplies 316 milliwatts of power. Current through elements in series is the same. I1, I2, and I3 all equal 19.8 milliamperes. As a result, R1 experiences a 3.6 volt drop, R2 experiences a 7.1 volt drop, and V3 experiences the remaining 5.3 volt drop. R1 dissipates 70.2 milliwatts of power, R2 dissipates 140.5 milliwatts of power, and R3 dissipates the remaining 105.3 milliwatts of power. For scenario 3, the closure of switch 2 has shorted out resistor 2, and all current will be routed around it. The source sees the reduced total resistance of the remaining elements R1 and R3 for a total resistance of 450 ohms. As a result, source current increases to 35.6 milliamperes, and the source supplies an increased amount of 568.9 milliwatts of power. Given increased current through R1, it experiences an increased voltage drop of 6.4 volts and dissipates an increased amount of 227.6 milliwatts of power. No current travels through R2, and as a result, it experiences no voltage drop, nor does it dissipate any power. Similar to R1, the remaining element R3 experiences increased current, and as a result, an increased voltage drop of 9.6 volts, and dissipates an increased 341.3 milliwatts of power. All right, that's about it for today. Hopefully you survived that last example problem. In conclusion, this lecture took a look at opens and shorts in series DC circuits. We learned an open anywhere in a series circuit halts all current flow, and given no current flow, no voltage will be dropped across any element. Any voltage rise will be dropped across the open. Shorts in series circuits, in contrast, remove the shorted element from consideration. Given a reduced total resistance, current through, voltage across, and power dissipated by the remaining elements increase, sometimes to dangerous levels. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.